Hi, I'm Miles Traer, and today I'm going to chat with you a little bit about energy. We use a lot of energy, especially here in the US, and demand for electricity is on the rise all over the world. But there's one often overlooked source of energy, geothermal, and you can find it right under your feet. Today, I'm visiting the lab of Roland Horn, one of the leading experts on geothermal energy resources. For those of us who may not be all that familiar with it, what is geothermal power?
Geothermal energy is the heat of the earth, and geothermal power is the extraction of the heat of the earth, converting it to electricity.
And where does geothermal sort of fit into the energy spectrum today?
So geothermal energy is extremely important in several specific places. California, for example, last year generated more electricity from geothermal than from solar or wind. But there are countries like the Philippines and El Salvador that get almost a quarter of their electricity from geothermal energy.
What are the biggest benefits of harnessing geothermal energy as opposed to, say, solar energy or wind energy?
The advantage of geothermal over wind and solar is it's not intermittent. It works all of the time. It doesn't matter whether it's night or day or windy or not windy, geothermal runs full time. Though geothermal energy runs full-time, extracting that energy can be challenging. Effectively, the heat flows through irregular cracks or fractures in the rocks thousands of feet underground. To capture that heat, engineers require an in-depth understanding of the underlying geology and where those fractures are. And that's where Roland Horn and his students come in. Horn is a pioneer of using nanotracers to determine the geology, temperature, and fracture geometry of potential geothermal sites. The attraction of using something like a nanotracer is that you can characterize what kind of geology you have at that particular site. That way you can address the methodology of the recovery to that specific geology. What you're seeing under his microscope are those nanoparticles tracing the geometry of a crack narrower than a grain of sand. To see how engineers use nanotracers and other technologies researched at Stanford, I traveled a few hours north of San Francisco to the Geysers geothermal field to speak with Stanford graduate Sarah Pistone.
This is the largest developed geothermal resource in the world. This whole site is a deep heat source, which is an old collision zone from when continental plates came together.
And so can you briefly explain how a geothermal power plant works?
Yes, here we get dry steam coming out of the ground. So we collect the dry steam in a network of pipes that gets routed to a power plant. It gets run through a turbine, spins a generator, and then it condenses out into a condenser, and then the water goes out to a cooling tower where it cools down and completes the process.
Sarah Pistone is just one of over 120 graduates of Stanford's geothermal program, which began nearly a half-century ago.
So the Stanford Geothermal program was founded in the early 1970s across three departments: mechanical engineering, petroleum engineering, and civil engineering, by professors Ramey, Kruger, and London. So it's been interdisciplinary and interdepartmental right from the beginning. It's become one of the most prominent places in the world for scientists and engineers.
Where do you see geothermal sort of going in the future?
So we are dependent for our future on enhanced geothermal systems, where we're going to improve the geology to make the geothermal reservoirs work better. So the future for geothermal energy is to develop technology to expand it in places that are not as advantageous as the ones used today.
There's some pretty amazing research and technology that goes into harvesting geothermal energy, and it's helping us realize geothermal's potential as an energy source all over the world. From Stanford, I'm Miles Traer. Thanks for watching.